So in this video, we're going to talk about the angles that are involved with circles. And so we'll start off here by first talking about intercepted arcs. So an arc is formed between two lines or segments that intersect the circle. We'll call that the intercepted arc. Meaning if I have this segment here and this segment here, those segments actually intercept the circle and create two intercepted arcs. Intercepted arc A and intercepted arc B. Both A and B are intercepted arcs. They're the arcs that are between the two lines. Alright? So we'll be using that term throughout this video. So first we'll talk a little bit here about what a central angle is. And we talked about this last time. A central angle has a vertex at the center of the circle. So if I draw something like this, we have the vertex here that is the center of the circle. The angle is equal to the arc. So if this angle is x, this arc is x. This angle would be x, and this arc would also be x. Okay? Now we can talk about what's called an inscribed angle, which happens when the vertex is on the circle. In that case, the angle is worth the arc divided by 2, or 1/2 of the arc. Alright, so what does that look like? It looks like that. And here's our vertex on the circle, and here's our intercepted arc. So if this is, let's say this is 40, the arc would be 80. So 80 divided by 2 equals 40. Or the arc divided by 2 equals 40. We have a tangent and a chord. So a tangent and a chord will look something like this. And again, in this case, the vertex is located on the circle. Since it's located on the circle, then our formula would be the same. The angle is equal to the arc divided by 2. So if we said that our angle in this case was 120, then we would have 120 divided by 2 will equal x. So x is equal to 60 degrees. So in both of these cases, whenever our vertex was on the circle, right, then we had 1/2 the arc. So these two are very related to each other. Next thing we'll talk about here is what happens when we have two chords. When we have two chords, of course a chord is when our two segments are inside the circle. So let's say this angle is x. Well, this would also be x because it is a vertical angle. So inside we have two vertical angles, and we also have two intercepted arcs. So if I call this the A, and this one will be B, then x will equal B plus A divided by 2. It'll be the average of the two. So what we say here is we call this the near arc plus far arc divided by 2. And this is when the vertex is inside the circle. We could also talk about two secants. If I was to draw two secants, with two lines that cross this circle in two places, what happens here is I get, again, two intercepted arcs. And we'll say this is B, and we'll say this is A. And we'll call this X. So the angle here, X will equal, we'll leave that, X will equal the far arc minus near arc, we'll leave it in words, divided by 2. And the formula for that would look like over here is X equals B minus A divided by 2. So when that's happening on the inside of the circle, you're adding the two arcs, the two intercepted arcs. When your angle is on the outside, you are subtracting the two arcs. Now, if I had a tangent in a secant, meaning my line is tangent here, but crosses through the circle here, I still have two intercepted arcs. There's still two intercepted arcs there, B and A. So again, X is going to equal B minus A over 2. Or again, what we call far minus near divided by 2. All right, the larger one minus the smaller one. Again, the vertex is going to be located outside of the circle. Now, if I have two tangents, you might have something that looks like this. So in that case, I still have two arcs, right? Maybe I put this second arc in green just to make it more obvious that we have B and A. Again, our vertex is on the outside, so X will equal B minus A divided by 2, or what we call far minus near divided by 2. And again, this is my vertex on the outside. So again, we see these three as being related to each other. Our vertex is outside, so we subtracted each time. Our vertex was inside, so we added. Now I want to talk a little bit about the center. If it's on the center, it's technically kind of on the inside. So let's look at that formula. If it's on the inside, you could do x plus x divided by 2, and you would get x again. So really we're looking at kind of three different situations. And I kind of want to explore that a little bit here on the next page. So if we're looking at this, right, let's say this is broken up nicely. This is 90 degrees, and this is 90 degrees, and this is 90 degrees, and this is 90 degrees. So when it's right there in the center, right, we have 90 plus 90 divided by 2, and we get 90 degrees, which gives us our two arcs. But as we pull that arc, that vertex, away from the center, right? As I pull that away from the center, even if this arc remains the same at 90 degrees, this arc will have to get smaller to be able to maintain. So let's say this goes down to, let's say about 30 degrees. Well, these are still x. They still have to be equal to each other. So what's it going to be? Is it going to be 30 or is it going to be 90? And actually what it'll be is the average. 90 plus 30 divided by 2. So you end up with 120 over 2, which means 60 degrees. The central angle has to be 60 degrees. So it's the average of the two. So as we continue to pull that vertex from the center, we can keep pulling the vertex until we get all the way to the edge. Right? As soon as we get to the edge of the circle, we now only have one arc. Because at that point, there is no arc. Or in essence, the arc is now 0. So if I'm looking at the same formula, 90 plus 0 divided by 2 really just becomes 90 divided by 2, which is 45 degrees. So again, it's still the same formula, it's still the same idea that as you pull away from the center, when you're in the center it's exactly equal. But as you pull away, one of them has to continue to get smaller and smaller and smaller. And the angle is your average between the two. Until you reach that point on the circle where the small angle has now become 0. And that can just simplify to half of the arc that's left over. Well, what happens when we move the vertex outside of the circle? Once you move to the outside of the circle, if we're thinking about this as getting smaller and smaller and smaller until we get to 0 on the circle, well, what type of numbers are less than 0? Those would be negative numbers. So if this used to be a 90-degree arc here, this arc is now considered to be a negative 20. Of course, the arc is in itself is positive, but the way we treat it is as a negative. Then our formula becomes 90 minus 20 divided by 2, or 70 divided by 2, which is 35 degrees. So, as we see, it's really the same idea. Just thinking about what happens as you pull that vertex further and further and further and further away from the center. So when you get to the circle itself, it becomes 0. When you move outside of the circle, as in this case, you treat it as a negative. The arc is still positive, but you treat it in the equation as if it was a negative 20. So you subtract it. So hopefully that kind of reinforces and allows you to understand what we're doing with these. And I just want to talk a little bit about these special cases. And this just talks about that two inscribed angles that intercept the same arc are congruent. Right? So if A intercepts this arc of 110, then angle A will equal 55. Angle B intercepts this 110 arc, well then angle B has to equal 55. So you can do all that work, or just realize that angle A will always equal angle B. If they intercept the same arc, then they will always be equal to each other. And we kind of see why that's true. We call them congruent since I didn't put the measures. Be correct. All right, well, thinking about that, there's just another natural logical conclusion that if my arc is 180 and it's inscribed, well, obviously half of 180 gives me 90. So any time that a semicircle is inscribed, it will be inscribed by a right angle, 90 degrees. So keep that in mind if you see an angle that intercepts this semicircle. And the last one here is if we talk about angle A intercepting this arc here, which we'll call X, and angle C, which intercepts this arc, BD, right? And we'll call that Y. Well, we can see by the colors that X plus Y has to equal 360, because that makes up an entire circle. So then if I call this P and Q, well, P and Q added up have to be 360 divided by 2 because they're inscribed angles. So P plus Q has to equal 180. So that kind of demonstrates why opposite angles of an inscribed quadrilateral will always add up to 180. Opposite angles will be supplementary for any inscribed quadrilateral. Alright, so that's it for this video. Make sure you understand the things we talked about and be ready to practice some of these problems in class. If you have any questions, we'll talk about that in the beginning of class.